and one theorem on conjugate operator. So let us see what is the conjugate operator first. Mute your audio and video, no, please. Yeah, we shall start with conjugate operator. Conjugate operator. Let us take let N be a non-linear space, and let us take a mapping belonging to B of N. That is, T is continuous linear transformation, and our T is a mapping from N to N only. Domain and codomain both are N and N only. And this T is also called an operator. An operator. So what is an operator? Operator is nothing but a continuous linear transformation from a non-linear space N to itself. Then T star will belong to B of N star. That is, our T star is mapping from N star to N star, and T star is dash, that is continuous linear transformation. And how is this T star? T star acts on N star elements, and N star contains all functionals on N. So it acts on F, and F in turn acts on X, N elements. Right? That is equal to, how is this T star defined? T star is defined like this: F of T of X. And this is happening for all X belonging to N, and very important for all F coming from N star. And this N star, T star, is called conjugate of T, conjugate operator of T. Now, let us go to a theorem. Theorem is this. Theorem. There is an isometric isomorphism. Isometric isomorphism. From where to where? From B N to B of N star, which preserves what and what? The identity map, the identity function or map, identity map, and reverses product. So we have to prove that there is a function between what and what? There is a function between B of N to B of N star, which is isometric isomorphism. And also we have to prove that it preserves the identity and reverses product. Okay, proof. So what is B of N actually? B of N contains all operators. T, what is T? T is from N to N, and T is continuous linear transformations. Linear transformations. Okay. And similarly, what is B of n star? B of n star is nothing but all t stars from n star to n star, and t star is same thing, continuous and linear transformation. Continuous and linear transformation. So now we have to prove what? We have to prove that there exists an isometric isomorphism between these two. So I should first of all define a function. So we'll make it a small step. Step one. Step one. Step one. Step one. Let's define a function. Define phi from where to where? B of n to B of n star. Define phi. Phi of t is equal to t star. T star. And what is T star? T star acting on F, and F in turn acts on X is nothing but F of T. F of T. This is how the phi is defined, and T star is defined like this. Now to prove that TPT, phi is well defined. We should prove that phi is well defined. What is the meaning of well defined? This T star belongs to B of n star. We shall prove that T star belongs to, that is, we shall prove that T star belongs to B of n star. What is the condition to be in B of n star? That is to prove that T star is an operator from n star to n star, and operator means T is continuous and T star is linear transformation. Okay. So now we shall prove that, to show that T star is linear. We shall prove that T star is linear. Now let F and G belong to two elements from n star, and alpha beta belong to the field R or C. Consider T star, consider T star of bracket alpha X plus beta G close the bracket, then X equal to, by definition, this is nothing but function alpha X beta G E of X, because that is how it is defined. T star F X is nothing but F of T X. This is how it is defined. Because of that, the function is, in the place of F, I have this. That is equal to, so now just multiplying this, just like multiplying now. So alpha F T X plus beta G E of X. You can put the bracket also, no problem. Okay. And that is nothing but alpha as it is. Yeah, sorry for the disturbance, some technical error. So that is equal to alpha. So F of T of X is nothing but T star F of X plus beta as it is, and this will become T star G of X. Now X we shall write outside T star X plus beta T star G bracket for this and X outside, and this happens for all X. Okay, so we'll remove X now. So therefore, T star alpha X plus beta G is equal to alpha T star X plus beta T star G. So therefore, T star is linear. T star is linear. We have to prove it is continuous. We have to prove it is continuous. Next, to prove that T star is continuous. So we'll prove it is bounded. So we shall prove that to show that T star is bounded. Bounded and linear will give it is continuous. Okay. So consider norm T star. Writing the definition. The supremum T star is acting on F, very, very important. That's on all functionals. Norm F lesser than or equal to 1. Supremum runs over F. That is equal to supremum F. The definition of this now. So this is again supremum. Okay. Norm T star F on X such that norm X is lesser than or equal to 1. This supremum runs over X. I'm writing the definition of this such that norm F is lesser than or equal to 1. That is equal to supremum. I'm writing one supremum which is running over both F and X. So norm T star F X. I'm putting one set lesser than 1 and norm F lesser than or equal to 1. This is lesser than or equal to supremum. So we'll write the definition of T star, not less than or equal to. We'll use the definition, so it is equal to only. So the definition of this is nothing but F of Tx. Norm X less than or equal to 1 and norm F less than or equal to 1 by using definition. And now lesser than or equal to, so our F is linear and continuous, so we can split it now. Norm F, and again Tx can be split. Norm, so norm F outside and Tx. So norm X less than or equal to 1, norm F less than or equal to 1. Okay. Now again this can be split. So again less than or equal to supremum norm F, norm T, norm X such that norm X less than or equal to 1 and norm F lesser than or equal to 1. So this will be lesser than or equal to norm X is less than or equal to 1, norm X is less than or equal to 1. So only norm T. This supremum runs over F and X. So T is taken outside. The remaining is 1. So we have got what? We have got we have got LHS norm T star lesser than or equal to norm T. Okay, let us call it as equation 1. We are going to use this again, and this implies T star is bounded. T star is bounded. Bounded and T star is linear. Together will give me it is continuous. So therefore, continuous and linear. So therefore, this T star will belong to B of n star. Therefore, the function phi of T, which is equal to T star, is well defined. Now, we shall go to the next step, step 2. Now we are going to prove that this phi is isometric isomorphism. Now to prove isometric isomorphism, first we'll prove phi is linear. To prove that phi is linear. To prove phi is linear, what is phi? Phi is a function from B of n to B of n star. So let me take two operators T1, T2 belonging to B of n. Take two scalars alpha, beta belonging to R or C. Now consider phi of alpha T1 plus beta T2. This is equal to, by definition, this is nothing but alpha T1 plus beta T2 whole star. How is phi of T defined? Phi of T is nothing but T star. So phi of any function, any operator is nothing but conjugate. It's conjugate. So star. And this star is equal to alpha T1 beta T2. This is an operator. This has to act on X. F in turn on X. That is equal to, by definition, T star F of X is nothing but F of Tx. So star will go now. So alpha T1 of X. That is nothing but, so F of alpha of T1X plus beta, F of beta of T2 of X. You can put a bracket here. That is equal to alpha outside F of T1X plus beta outside F of T2X. And that is nothing but alpha. F of T1X is nothing but T1 star of F of X. And beta outside T2 star of F of X. Now what is common with right outside? So alpha T1 star plus beta T2 star, bracket for this, F X. Okay, this happens for all F and for all X. Therefore, we can remove now. So phi of LHS alpha T1 plus beta T2 is nothing but alpha T1 star plus beta T2 star. What is T1 star? T1 star is nothing but phi 1. T2 star is nothing but phi of T2. And LHS is alpha T1 plus beta T2 equal to this. Therefore, phi is linear. Phi is linear. So we proved phi is linear. Now we shall prove phi is 1. So next step, step 3. To prove it is, remember our equation 1, you should not forget equation 1. So step 3, to prove that phi is 1. So let us take two images equal to phi of x. By definition, this is nothing but T star, S star. This is nothing but T star acting on Fx is equal to Fx. Now using definition of stars, f of x, f of Sx. This implies f of Tx minus f of Sx equal to 0. This implies f of Tx minus Sx equal to 0 because f is linear. Next, minus Sx equal to 0. So this implies P of x equal to x of x. This is happening for all x. So therefore, T equal to 0. Conclusion, phi is 1, 1. We proved phi is linear, phi is 1, 1. Now the last step, step 4, to prove that phi is isometric. To prove that phi is isometric. That is, I have to prove that phi of T norm is equal to norm T. That is, what is phi of T? T star norm T star equal to T. We have already equation 1. We have equation 1 which says that norm T star less or equal to norm T. We have already proved this. The only thing is we have to prove the other way. So to show that norm T star is greater than or equal to norm T. So if you prove this is 1 and 2, I guess both are equal. Now to prove the equation 2, okay, consider, I'll take any element belonging to n, x is not 0, P of x is not 0, because x is not 0, P of x is not 0, and T is actually somewhere in only, no? That is, T of x also belongs to n, okay, and T of x is non-zero. Non-zero element of n is a non-linear space, n is non-linear space, by Hahn-Banach theorem. Hahn-Banach theorem, there exists a functional f0 belonging to n star such that this f0 belonging to n star f0 of this non-zero element, that is Tx is equal to norm of Tx, and norm f0 equal to 1. This is one of the application, the first application of Hahn-Banach theorem. So we have this. Okay, so now